Hey, great to see everyone, even Mr. Nello. You told me your name today, but I forgot it. So embarrassing. Anyway, welcome back to the Arduino AVR reverse engineering and whatever class, and great to have you back. I know last week has been last time has been a little intense, and this time is going to be too. So before jumping right into the deep water, I just want to say that I hope that you had a great week, and let me share my screen and just let me know in the chat if if everybody can see my screen as soon as I will share it in a moment. So screen shared. Let's just make sure that I can see the chat while I'm sharing the screen, and please let me know if you can see my screen. There are like LEDs. One of them should be blinking. Looks good. Thanks, Christina. Okay, so great. So last time we walked through a couple of instructions in assembly. We have met like this ASM statement and this horrible syntax with the things you want to write to and read from. And they had a few questions in the following Q&A session. I realize this is an awkward syntax. Like I'm still not used to it, and I make errors every time. It doesn't look like C or C++. It's strange, but anyway, it is what it is. And today, in a few minutes, we are going to see another way to write assembly, which is a bit less awkward, in my opinion. So last time we started talking about arithmetic instructions. Specifically, I think this is the instruction set, and you have the link in this document. And just so everybody has the link, I just copied it to the chat. So the instruction manual is linked from here, the previous class, documents and resources. And now we are in the third class, and we'll have a few more resources soon. So last time, I think we stopped on the inc instruction. It's the first instruction that is doing arithmetic. Before of that, we just loaded data and save data and move data between registers. So where is the inc? Okay, increment. So we did it, but let's do it real quick again, just as a refresher. So this is the name of the instruction, the description. It adds one, not -1, to the contents of the register and places the result in the same register. And you can see like it can work on RD, so inc RD, and D can be between 0 to 31, so it can work on any of the registers. And if you need a refresher, there is like a quick summary here about the registers that we have in AVR. There is actually one more, which we will probably touch today, the stack pointer, but we'll get to that. Inc is and all the other arithmetic instructions actually updates this status and flags register that we have seen last time. For instance, it updates the Z flag, the 0 flag, and that flag is set to 1 if the result was 0. And there is like this flag N that tells us if it was negative, and if there was an overflow from signed integer to unsigned, like if it was a signed integer and there was an overflow. But let's not worry about this for now. Let's just worry about Z, because it's going to be the most useful. Anyway, let's just do a quick demo. So let's say we have value. Actually, I want it to be just 1 byte, uint 8. So value is 5. Never mind. Let's also set up the serial output so we can see the output. And let's serial println value. And obviously, this will be 1. Okay, why did that happen? interesting. I didn't expect that to happen. That's strange. Yeah. I don't know why it prints 1. Something is wrong. Anyway, let's try to refresh the page. It may or may not help. And try that again. Surely missing out something. Okay, interesting. Oh, yeah. It should have been serial.begin, not .println. So it tries to print that number, and then we haven't set up the serial, so it doesn't continue printing. It just sends out the first character. Okay, so yeah, now this looks more sane. So we have this, and it prints 5. Perfect. And now let's just increment it. And we don't really know which register the compiler uses for this variable. In fact, it will probably optimize this to read as just serial println 5. But if we use the read, we can actually force it to be copied into a register. So we want it to be in a register and a value. And then we can inc the first operand, which is R. And this doesn't work because the compiler doesn't actually expect us to update value. So we could use this syntax, which tells it we want to write back to R. But if we wanted to use the same register for both, we can actually write here, instead of this R, just the number of the argument. So 0 is like the same as this. It tells the compiler, I want you to use the same register or the same constraint as I defined here in this read. So basically, it will read the value from this register and then write it back to the same register. And if we run it now, we can see that we got 6. So basically, that's what inc does. And like increment, we also have decrement, which is -1. And the decrement is pretty similar. Actually, we don't even need to look at the manual because it does the same. To make it a bit more interesting, we can also see how it affects the flags. Yeah, multi-line assembly statement. Close the multi-line. Yep. Okay, so we have this trick where if we have this break, it will print out the registers. And specifically, when we decremented this value, we can see there were a bunch of registers set, like the carry and the H. If we use increment again, we can see, yeah, we can see it's basically the same flags that were set. And if we have here this value, then after incrementing, it's 1 byte, so it overflows to 0. And we can see that the Z register was set. So just like the manual says, where is increment? That's increment, yeah. If the result is 0, then we set the C flag. So we can verify here that it actually worked. It actually set this flag when the result was 0. Just like inc and add, we have instructions to shift right and shift left. So for instance, let's say we have this value of 4. And we want to shift it left. So basically shifting left is like multiplying by 2. So logical shift left, 0, the register name, that's 0%0. And we can see we got 8. So basically multiplying by 2. And then we have shift right, which is the equivalent of dividing by 2. And just like before, they update the flags. For example, if we had 1 here and we would divide it by 2, we see that the 0 flag has been set and a bunch of other flags. So basically, these are like the basic operations of shifting right and left, incrementing, decrementing. Another useful one is com, which is just complement, which means bitwise not. So if we have, for instance, 0, the not value of 0 is 255. So bitwise not. We can actually see it. Yeah, basically bitwise not. Again, you can check out the instruction manual and see how many cycles it takes. One cycle, and carry is always set to 1 after not, and this one is always cleared, and 0 is only if the result is 0. Basically, they all the instructions, the arithmetic instructions, have a similar effect on the flex. Okay, and then the next instruction, this one is, I think, it's a bit unique. I'm not sure if there is such instruction on the x86 or other architectures. It's called swap, and what it does is basically swapping the nibbles of a byte. So instead of 42 hexa, once we run this, we can see that now we have 24. So it just swaps the digits, the hexadecimal digit of the number. So another useful instruction. And let's just quickly write down the instructions that we covered, that so that we won't forget. So we had inc and dec. We had then LSL, LSR, shift right, left. And then we had comp, which is bitwise not, and swap, nibbles. So these are all unary instructions. So they get one value or one register, and they work on the value in this register. Another instruction, which is a binary instruction, is SBR, and there is also CBR. And what they do are they let us set a bit on a register. So SBR sets bit in a register. Basically, we give it a constant, k, some kind of constant, and it will set all the bits in the constants on the register. So it will do a bitwise OR, logical OR, between the contents of the register and the constant. And this way it will allow us to set some bits in the register. For instance, we have this value 42. We can set bit number 1, and then it will be 43. And if we set bit number 2, which is already set in this case, there won't be any effect. We'll get the same result. So SBR sets a bit. We have SBR, and CBR similarly clears the given bit. So this will actually clear that bit number 2. And then we are only left with 40. And we can also clear this bit. So basically, CBR with this mask will clear this bit, the 40 hexa. That's the second most significant bit, and we will be left with 2. So CBR is just sets and clear bits. I'm hearing something in the audio. Is there anyone who? Okay, probably just an artifact. Cool. So these are like all the basic operations that work on a single register. There are probably a few more like neg, but they aren't really interesting right now. And just like we did here, you can find them in the manual if you encounter them or need them. And then there are a few operations that work on two operands, like adding 2 numbers. So let's, for instance, value and value 2. So we want to add 2 and 40 hexa, and then we will add it as another register we read from. Actually, let's give it a name. So it will be easier to follow. And then we add to the first register, this one, we add the value 2. Actually, let's give this one a name as well. Let's call it in1, and here in1. It's the same one, and this will be in2. And then add in1, in2. And hopefully we will get here 42, as it will be adding the two numbers. And it's also, let's make this a bit bigger. Yep, it's also, one more, yep. It's also updating the flag. So in this case, the result was not 0, but for instance, if we add 2 to FE hexa, then it will overflow and we'll have 0 and carry. So the result was 0. That's why the 0 flag was set, and carry because FE plus 2 actually equals 100 hexa. So this is the result, but we got an overflow. We got a carry, another bit to the left, which was omitted. So it ended up in the carry flag. Just like adding two numbers, we can also subtract two numbers. So this will basically do value minus value 2. So the result is 1, or 22 minus 1 is 15. That's actually hexa, so that's right. So it should be 21 in decimal. So adding and subtracting, add and sub. Oh, thanks for this comment, Mikhail. Yeah, and I think a few more useful are like bitwise AND, OR, and XOR, exclusive OR. One thing to note, they don't call it XOR, they call it exclusive OR, EOR. And let's just do exclusive OR between two numbers. And XOR, when you XOR two numbers that are the same value, you get 0. So let's try that. And yeah, we can see we got 0. Also, the 0 flag is set because the result is 0. And in the OR, they work similarly, get two arguments and two registers, and update the first register with the result of the operation. So we have also AND, OR, and EOR, which is XOR, which are just bitwise operations. Cool, thanks for the addition, Mikhail. Okay, so that's it with arithmetic instructions. And right now we can, there are a few more, like multiplying numbers and dividing numbers, and I encourage you to check them out, like mul, and I think there is one for division. I'm not sure, actually. I think there isn't division in the AVR, as far as I remember, just multiplied. Yeah, there isn't, just shifting if you want. If you want to divide numbers, you have to write a code for that yourself. Isn't that hilarious? Anyway, so there is instruction for multiplication, add with carry, subtract with carry, and all of that. But let's go, oh, what happened here? Let's go over to the more interesting stuff. So we know how to load data from the memory, how to save data from the memory, and how to perform arithmetic operations on it. But what about control flow? So the first thing we're going to see is actually this useful instruction. It's called jump, and it lets you go to a different location in the program, just like the go-to keyword in C that you should never use. So basically the syntax is jump and where to jump. And we can give it an offset like 100, and it will jump to location 100 in the program, but we don't really know where we will end up unless we write all the instructions and figure out their calculator addresses. So we can use labels like let's jump to before, and before just define before just after the jump, and that would create an endless loop. So if I run the program, you can see it sort of got stuck here. It never printed the value, and the break was not executed. Or I can jump forward. Let's jump to after, and yeah, so after the break, and you can see that the break didn't execute, so I didn't get the debug info on the console. So yeah, so that's jump, and by itself it's not very useful. So how can we make some kind of conditional jump if? And the answer for that, there are like a bunch of instructions which are called conditional branches, which are just like JMP, but they jump depending on the value of the flags. So they are defined here in conditional branch summary. And basically there is a bunch of them, and we'll go over it in a moment. But first of all, you need to, you can see here that they all like look at the flags and decide based on the flags on this condition whether they should jump. For instance, we can jump if it's 0, or jump if not 0. Like if the 0 flag is set or if it's not set. And what we can do, for instance, so we know this EOR only will return 0 if these values are equal, because that's what XOR does. We have just seen that. So for instance, we can say instead of jumping over break, we can say that we want to jump to after only if the result is not 0. So that's BRNE. Let's do that. So now when I run the program, we can see that interesting. Oh yeah, it's not 0, so it didn't jump. So the result is 0, so this jump didn't happen, and we had this output. But if the result would have been different, like 54 and 50, which would not give 0, then it would take the branch because the result is not 0, and we won't get a debug output. So basically, once we perform some kind of arithmetic instruction, we can use the result in the flags in order to conditionally branch to another place. And that's how we implement conditional logic and also loops. And before we see a more complex example, I will show you one more useful instruction, and it's super useful with those branch instructions. Because usually you want just to compare two numbers and you don't care about the result. Here, the exclusive OR actually stores the result in one. So there is another instruction called CP, compare, and it compares two registers, and none of the registers are changed. And all conditional branches can be used after this instruction. So basically, this instruction just checks, compares these registers and updates the flags, whether the result was negative or positive. And the nice thing about it, you don't really have to worry about the meaning of the flags. If you check out the table that we have seen before this summary, we can just like call compare with two registers and then choose the condition that we want. Let's see how we do that in practice. So we are going to define a new function. We'll call it max8, and this function gets two arguments. Let's call it left and right. And basically what it's going to do, it's going to compare them and then return the maximum of them. So let's have another variable to hold the result, and then we can just copy this. That's what I always do within my assembly. I just copy it instead of writing this from scratch. And we can start writing the logic here. First of all, we want to store the result into result. And we want to read from register left and another register right. And let's call them right and left in assembly as well. So these are the names we'll use inside the assembly. These are the variables we are reading from or writing to. And then we are going to compare them. So comparing left and right. And I have two rights. Do I? Where? If you mean here, oh, here, yeah, right. Thanks. Thanks, Maru. And if I have, so I compare these two numbers, and now I want to decide what to do. So basically, if left is bigger, store left into result. Otherwise, store right into result. So the first thing I want to do before I jump into the table, I want to see if I'm doing this with signed integers or unsigned integers. And in this case, I'm using unsigned integers. So when I'm looking at the table, I will only look at this section, which is talking about unsigned. I don't care about the signed now. I'm looking at the signed section. And now I want to check if RD is greater or equal than RR. And for that, I can use this instruction, BRSH. Yeah, funny. So BRSH and so BRSH, and we'll go to left is greater. Left is greater. So if left is greater or equal, then we will, S8 stands for same or higher. And I guess if we will check, yeah, same or higher. Thanks, Mikhail. Yeah, and that's also, and other branches. And we also had a CP compared to registers. Okay. So if this is same or higher, then we are going to this left is greater than EQ. Otherwise, we are just, we know that right is greater, so we will move, we'll copy it into result, right? And if left, and we don't want to execute the code in left is greater, so we'll need to use jump here and jump to the end. So jumping to the end. And if left is greater, then we just want to move left into the result. And now, hopefully, we have a function that compiles and works. We don't need those comments. I will compile it. And let's actually print some test cases already. So max 8 of 10 and 20, and 20 and 10, and some edge cases like 0 and 255, 0 and -1, which is 255, because these are unsigned integers. And let's run this. And we can see that it doesn't work. Maximum of 10 and 20 is not 10. This works. So it seems to always return the left argument. Let's try to figure out what's the reason for that. Yeah. First of all, let's check. So let's call it only once with, actually, here it should return 20. So let's call it only once and then add a break here so we can see what's going on. And we can see that it took the branch. Interesting. Oh, it didn't. It took the branch. Yeah, left is greater, even though the right value is greater in this case. because if we put a break here, we can, oh, it doesn't print a debug output. Interesting. Interesting. We don't get any debug output at all here. Did we call? Let's see. Just a sanity check that we get into this function. Yep. And let's print left and right. Yeah, it works. So what happens with the ASM statement? And I have an idea what it might be. No. Interesting. Let's just narrow it down, for instance, for a second to. Okay, that's interesting. One more thing that. Oh, okay. So this is something that sometimes happens. The compiler figures out that this assembly is not needed for whatever optimization reasons and just removes it altogether. So using the keyword volatile can actually help here. And the reason the compiler optimized this output is this code out is pretty simple. We do the calculation and store it into result, but we do nothing with result. So basically what happened is that the compiler saw this code and then, okay, it does something, stores the result into this variable, but nobody is using this variable. So I'm just going to optimize that out. And that's the reason why when we called break, we didn't see anything in the console because this code was never emitted. And then volatile is a special keyword that tells the compiler, you know what, never optimize this code away. And when we added volatile, we can see that this code is executed and we have seen the break. And this helped me figure out that normally this code didn't execute, it was optimized out. And then I realized that this is because we forgot to return result. So let's do that. And let's return all the test cases. And now let's also remove this print so it won't confuse us. And now running it again, we get expected results. So 2020 and 255, that's the maximum. Now, just to show you what would happen if we use the signed instructions. So that was signed branches. So instead of using BRSH, we could have used BRGE, which is the signed version of this condition. Then we would get something different. Suddenly, 0 is greater than 255 because this number is no longer interpreted as a positive integer. It's interpreted as -1. So yeah, so BS is adding in the chat that volatile is also useful for the same reason when debugging, because often some parts of the code are optimized out and no longer match the C source. That's true. And you can also define variables volatile. So if we had this variable volatile, then assembly would, the compiler would see we are referencing it inside the ASM statement, and it would not optimize it away. So I think if you're writing inline assembly, it's best to start with volatile probably, and then remove it. And as you have seen, it really helps you catching bugs if you see that the behavior changes when volatile is not there. And yeah, somebody also mentioned interrupt. So defining a variable as volatile is also useful if it's accessed from interrupts, but that's out of scope right now. So yeah, so we implemented our first logic in assembly, and there is a little problem that you should be aware of with those labels. So actually, let's say I want to change this code and call this one end as well. And I will try to compile it. And actually it did compile because I think this one was optimized away. Yep. now it wasn't. Again, I calculated something and I didn't print the value. I didn't use it, so it was optimized. So that's why it wasn't compiled. But now it was compiled, and the assembler tell me "and" is already defined. And that's an issue with those labels because they are global in the entire source file. So just like that, I couldn't use a label that matches the name of function. Like if I called it setup, for some reason it worked. Probably because that's a C++ function. We'll talk about it in a moment. But if I called it, for instance, I think digital write, for instance, is a C function. Let's check that. No, interesting. Or maybe start. Yep. So for some reason, I guess the C++ name mangling doesn't changes the name of the function. So it doesn't make a problem, but still they are global. Like I can't use the "and" in two different places. That would fail. So there are a few ways around it. One way is just use the name, the function name in front of each label inside a function, something like that, to sort of guarantee uniqueness. That could work. And there is also a syntax for local labels. So instead of calling them names, I just give them numbers. So that would be 1 and that would be 2. And then instead of branching to 1, I need to tell it whether it should branch forward, go down, or branch backward, go up. So in this case, I want it to go down. So 1F means 1. Look for the closest one down. And here I want to branch to 2F, so go to the closest 2 down. And then I can compile it happily, and it works. And if I add another one here, this branch would still go to this number 1 because it looks for the closest number 1. So that's why they are sort of local, and you can have up to 9 of those, so from 1 to 9, and they are pretty useful for. Wait, I wanted to remove that one for shorter code snippets, and for longer one, I usually just break it down to smaller functions. There is also another syntax that lets us add a unique number. So let's call it greater. That's the syntax, but it only works in inline assembly. So I usually don't use that syntax. It just adds some unique random number that is unique per each ASM statement or something like that. So it exists, but I usually don't advise using it because then the code only works in inline assembly. Cool. So we had max 8, and now I will briefly mention. So we had CP. Oh, thank you. I will briefly mention a few more instructions that are useful. So there is, for instance, CPI, comparing with immediate. Just compare a register with some value instead of another register. This is a nice shortcut if you know you just want to compare with some value, so you don't have to copy that into a different register first. And there is also a bunch of instructions that are unique. So immediate. There is also a bunch of instructions that are unique to AVR, I think. And these instructions are called skip. So we can skip the next instruction in some conditions, like if a specific bit in the register is set or cleared. So if this bit is set or cleared, it will just skip the next instruction. But they are useful. I mean, you can get the same thing. You can do the same thing with branches and bitwise operations. So they are useful, but I mean, you can find them here if you need them, but we are not going to go and use them right now. And the next thing I want to do actually is to get rid of this ASM, to stop writing inline assembly, because when we wanted to test just 1 or 2 instructions, that was fine. But now we have a whole function that is basically assembly, but we have to write all this fancy syntax just to get it to work. And for that to work, we need to, if we want to define our own functions in assembly, we actually need to know how the compiler expect a function, what it expects from a function. And we can find this information in here, yep, in the AVR GCC wiki. And this is a section called ABI, Application Binary Interface. Let's put it in this document. So that's the text would be GCC, AVR GCC application binary interface. And the application binary interface basically defines how the compiler uses the registers and how it calls functions, how it passes the arguments. So it's all defined here. And we can see like it defines the sizes of types. So int is 2 bytes, long is 4 bytes, long is 8 bytes, etc. And there is a bunch of other things regarding types. But then there is this section about register layouts. And there are like a few interesting bits here. First of all, values that occupy more than 1 8-bit register, so 16 bits or 32 values, always start in an even register. So if the compiler needs to store a value in 2 registers because it's too big, it will always start with an even register, like R30, R22, R4. And then we have a few registers that are spatial. So R0 is used as a scratch register that need not to be restored after its usage. So if we want to use some temporary register inside inline assembly, we can actually use R0 because it's a scratch register. The compiler doesn't expect it to preserve its value. So that's okay. The only time we need to take care of it is inside an ISR. And if we are using inline assembler, we can use this macro instead of writing R0. And R1 always contains 0. So the compiler needs the value 0 in many different cases. So it just stores this value in this register. And whenever it needs a 0, like to end something with 0, to add, to multiply by 0 or whatever, it just uses the value in R1. So you can always, if you are running inside this C environment, you can always assume that R1 is equal to 0 and you must never change its value. And then there are a few other registers. So these registers are call clobbered. This means that any function can use them and it doesn't need to restore the content. So if you create your own function, like we did here, you can basically use these registers for free. And you know that the compiler doesn't really care about their content. If we had non-assembly code here, then that would have probably been different. But if it's a pure assembly function, then these registers are free to use. And then the remaining registers are cold saved. So if you change them, you must store them to the memory or to the stack, as we will see. And then before your function returns, you must restore their original content. So if you want to write code that will work in harmony with this environment, just like we did here, and we had to respect the fact that we are running inside the GCC compiled code, we have to respect this constraint in order not to to interfere with the other code that GCC compiled for us. And another interesting piece of information is the calling convention. So I won't go over this long text. It's a bit cumbersome, but basically defines how parameters are passed to functions. And I think this summarizes, this example summarizes this pretty good. So we have a function that returns int and take 2 arguments, a character and a long value. And we can see that the first argument will be passed in R24, and then B will be passed in these 4 registers, so 20 to 33. So in a nutshell, if it's 1 or 2 bytes, then the first argument will always be in R24. And if it's 2 bytes, like UN16, it will be also, the high byte will be in R25. And then the result is stored R24 LSB and R25 MSB. And like this example is useful for most of the functions that you will create. They will probably not take more than 1 or 2 arguments. If this argument wasn't long, if it was like a character or UN16, it would start in in R22 and not R20. But to really understand how to calculate this, just you can go over this and it explains the algorithm. Okay, so Julian is asking whether there is a reference for the assembler label format. As far as I can tell, I couldn't really find a coherent reference. These 1F and 2F, I will look for it for the next time if I can find something better. But basically, everything is global except for those local labels with numbers. That's what I have found. So cool. So now that we know how the compiler passes arguments and what it expects from functions, we can actually create our first pure assembly functions. And I think I haven't tried it, but I think we can't really do this like here. That would probably not work. Just emitting assembly code, random assembly code globally. Oh, it works. So there might be, it might work. You may be able to define functions, pure assembly functions, using this ASM statement. I haven't tried it, but what I usually do, which makes a lot more sense to me, is just to create a new file with assembly code. So let's call it Hackaday. And the extension has to be S, so it will be assembled and not compiled with a C compiler. And then let's start with a really simple function that basically we want to create a swap function that will swap the nibbles just like the instruction does. We don't have that operator in C, so let's create a function for that. So for that, we just need to define a label like we did here, and that would be the name of the function. And then we remember that, somebody asking about the extension, that's an uppercase S, Hackaday.uppercase S. So we said that the first argument will, if it's 1 byte or 2, will be passed in R24 and the result in R24 as well. So basically, we just need to swap R24 because arg1 in R24 result in R24. It's the same register, so we can just do whatever. And then the other thing we need to do, we need to write ret, which means yeah, there is no syntax highlighting here or autocomplete for assembly. I will probably fix it over the next few weeks, but for now, we'll have to imagine it's colored. And then in order to be able to call this function from another module from the main sketch, for instance, I need to say to declare that it's a global. So it's sort of a way to say that this label is actually exported from this file. And that's all we need to do from the assembly side of things. And in an idle word, we could just say something like, let's say this. Let's remove those. Actually, let's keep them for later. So, and let's remove all this clutter. We don't need it anymore. Yeah, maybe I will just copy this to the document so you will have it as a reference later. Okay. And in an idle word, we could just say something like serial println and then println swap, let's say 42 and expect it to be 24. But unfortunately, the compiler said, I don't know about swap. What's swap? And in order to make the compiler recognize that function, we need to declare it. So just tell it there is a function called swap. It returns uint8, and it also takes the uint8 argument. And the reason we need to do it is so that the compiler know which registers to use, because this depends on the size of the argument, which registers it should use to pass this value. And if we run it, it still doesn't compile. It says undefined reference to swap. And that's pretty tricky. The reason it does it is because it actually expects a different function name. I don't remember what's the name of this, but C++ adds some sort of decoration to the function name. So it's something like swaps underscore something. I don't remember the exact syntax because the function name also, the compiled function name also includes information about the types of the parameters and the return value. So in order to fix that, we can just say this is a C function, which is a bit of a cheating because it's an assembly function. But basically what this does, this tells the compiler, hey, just call it swap. Don't do any name mangling. I think that's what it's called. Just look for a function called swap without any additions or changes. And now if we compile it, it actually compiled and we got a correct result. So that was our first assembly function. And now I want to show you how we take this max8 and implement it in inline assembly, how it would look in assembly. So basically we have max8 and just like before, let's make it also global max8, arg1 in R24, arg2 in R22. So going down by 2 for each argument, as long as they are 1 or 2 bytes. And then we just define it. And then we don't need all the variables. And we don't need all this clutter. We just need to do something like this. We compare arg1 with arg2. If it's greater, then jump here. Otherwise, we move, we copy result. So R24 and R2, that was R22. So we just copy the second argument to the result. But actually, if we are here, if they are, this is greater, we have to copy R24 into R24, but we don't really need this, right? So basically we can remove it because it doesn't do anything. And now we can see that jumping to F actually does nothing because it just jumps to the next instruction. So we can remove it as well. and the label as well. And then the last thing we need is just the return, the red, to tell it to go back to the function that called us. So just changing this to lowercase. So basically now compare this with this, and I think you understand why you want to avoid inline assembly whenever you can. Like if you can just write a function straight in assembly, then it's much shorter, easier, and you don't have to work very hard to cooperate with the compiler. And now let's just make sure that it still works. We still need the function signature though, like we had for swap. And let's have all these test cases again. And we can see it still works. I don't know if you remember, but we are getting here 0 instead of this, because this is signed. We change it to be signed comparison. If we go back to BRSH, then it will be unsigned comparison, and this one will be greater than 0. So yeah, that's how we are going to write assembly for the rest of the course. No more having to fiddle with those with this awkward syntax. And one more thing about function calls. So whenever you call a function, like here, where was that? Yeah, like here, or calling swap, it's actually pushing the address of the return address, like the address of the next instruction, into the stack. And this stack is like a data structure that starts at the end of the memory and it goes down. So whenever we are calling a function, there is a new value at the bottom of the stack, and then the stack pointer goes decrements to point to the next location in the stack, which is down in the memory. And then what ret does, it basically takes the instruction from the top of the stack. So basically, it's the instruction that the address that was pushed when we call this function, and it jumps to that instruction. So it removes the top value from the stack and sets the PC, the program counter, to that value. And that's how calling functions work. And we have a few utility functions. So in this utility instruction, so in this case, we had really simple functions and we didn't really need to use any temporary registers. If we needed some temporary registers, we could have used all of those scratch clobbered registers without worrying too much, because the compiler doesn't expect us to save them. But in the next lesson, we are going to implement Fibonacci, which is a recursive function, and then we'll have to have some temporary space to store the registers while we call the function recursively. And then we'll see how we use the stack for that with the push and pop instructions. But I think that would be for the next time. So let's do a quick review of what we had today. So we learned about a bunch of new arithmetic instructions, and now we have also ret. And then we saw how to compare numbers, and how to define functions in pure assembly, and how to return from functions. But more importantly, I think we learned about, thanks for the reminder, we learned about the AVR GCC ABI, which lets us call our assembly functions from C. And we can also do the opposite, like we could also call some of the, actually we have one more minute, so we can do that. Let's make swap also turn this LED on. So basically we want to call digital write, that's a C library function, and we know it gets a pin number and a high or low. So that's pin 13, first argument, hold the I 2413, LDI R22 R32 1 because it's high, and now our yeah, it won't swap anymore because now we are destroying the value in R24. But now our swap function should actually turn on this built-in LED. Let's see that. Yep, it worked. So we can, now that we know the ABI, we can define functions in AVR, in pure AVR assembly, not the inline assembly, and we can also use that to call C or C++ functions from our assembly code, which lets us basically integrate the two pieces. So yeah, we can also add call to the list. We now know how to use it. And the really important piece here is the ABI. So that's it for today. I hope it was intense, but not too intense. And yeah, I will take question in a moment. Before that, last week we announced that we will have a final project in the course. And I've put together a description of the project. It's basically building a Pong game in AVR assembly, like we have here, but from scratch, without using any of the library functions. And right now, I guess you still don't have all the information you need in order to create this game. But after lesson number 5, you should have it. So we still have a long way to go in the next 2 lessons. But this is just to give you a general sense of the final project. And if you want to get a certificate from Hackaday, then you would have to do that. And if you have any questions about instructions, just or about anything here we learned today, just hit me on the Hackaday chat or the Discord channel of Walkway. I'm always there waiting for you. I'll also add this link, even though it's, I will probably add some more information over the next couple of days. That would be final project. Oh, I love this. This responses challenge accepted. Intense, but not too intense. Perfect. Thanks. Project description. Yeah, I'm looking forward to see what kind of pongs you will make.